Electromagnetism test. So the first two questions, I think everybody got those correct. Then the second question, part C, was about the pros and cons of a wind farm. There were some quite waffly answers in here and some minor details. So as a teacher you need to be really clear about what the main points are here. So there's a pretty wide choice, but arguments to persuade people that a wind farm is a good idea. It's renewable energy, so it will not run out. Low levels of CO2. In this case you don't need to say it's a greenhouse gas, but I guess that's a key bit of information. It's not zero CO2, and you would lose the mark if you suggested it didn't have any pollution associated with it, because of course there's maintenance costs and things like that that affect emissions. Zero fuel costs though, that's fine, and you can use the land underneath wind turbines for agriculture. Reasons against a wind farm: so noise pollution and visual pollution. You need to be careful of the wording there. Coal-fired power stations are both noisy and ugly, so the reason why a wind farm's a problem is that it's to do with the location. If you say noise pollution and visual pollution, then that covers that idea that the noise is a problem because of where it is. May harm birds, expensive, that's because of the capital costs. Some people put for supporting wind farms that it was cheap, and that's not the case. Electricity produced by wind farms is more expensive than produced by burning fossil fuels, so just be a bit careful with that one. Actually, the key point about wind farms in terms of their large-scale use is that they're an unreliable energy source, and I guess that's an important point to get across, and that was only in one or two people's answers. I was a bit surprised by that. The next question, which is number 4 on the paper, how can you tell from the diagram that this is a step-up transformer? Secondary coil has more turns than the primary coil. As always, be careful about the use of the word turn and the use of the word coil. There were quite a few answers that said 1.5 volts on the primary and 6 volts on the secondary. There's a bit of an argument there that just because the lamp is supposed to be a 6 volt lamp doesn't necessarily mean that that's a step-up transformer. I think that's a little bit harsh, but that was how the mark scheme was organised on this particular occasion. What materials used to make the core of a transformer? So that's a standard answer, laminated iron core. You only need the word iron actually because it's after the material, but I'd be encouraging kids to just always say laminated iron core. You're never going to lose any marks for that. 2 ways in which the design of the transformer could reduce the brightness of the lamp. So fewer turns in the secondary coil, more turns in the primary coil. Those feel a little bit like they might be opposite versions of the same thing, and in a GCSE or A-level paper you won't get 2 marks for saying one thing both ways round. But actually it's not like that here. If you knew nothing about transformers, then it wouldn't be completely obvious that more turns in the secondary was the same as fewer turns in the primary, or vice versa. There were quite a few answers about turning down the voltage of the power supply. That's not an appropriate answer because it asks about the design of the transformer, and the power supply is not part of the transformer. This question was answered well, I think. And then there's another question about the national grid. So that's similar to an earlier question. Why do the power stations generate AC and not DC? That's because transformers only work with alternating current. It'd be fine to say transformers only work with AC, but it's quite nice to show that that means it's a current that's changing direction, because that's directly related to the use of the functioning of a transformer. That's a really standard GCSE question, so if you're ever asked about national grid and why it's AC, the answer is always because transformers only work with AC, or transformers don't work with DC. You can answer it either way. State the purpose of transformer A and explain why it's an essential part of the national grid system. So for 3 marks, any 3 of these points. It increases the voltage, or you can say potential difference there if you want. So there's a smaller current So there's less heating of the cables because of the smaller current, and that means it's a more efficient transmission, or there's less energy loss, would be absolutely fine for that last point. That's a different set of things on the mark scheme from the earlier question. This was the second question in the paper. It's exactly the same diagram. The question here is explain why step-up transformers are used in the electricity distribution system. That's only 2 marks, and for this one there was no mark for saying that it increases the voltage. You just had the mark for saying it decreases the current. I think that's just the difference between a 2-mark question and a 3-mark question. The key idea is that because you've got a small current, you get less heating. Because you've got a small current, you get higher efficiency or less energy loss. The high voltage is why you've got the small current, and it's not, so it's like an extra step in the explanation. So because this is 3 marks, you can put that extra step in and get credit for it. So again, that's a kind of subtlety of how the GCSE questions are set up. The fewer marks there are, the more critical it is that you get the key point. Sue's designed for a simple wind speed gauge. You could make this at home if you wanted to. There's a little project for the weekend. So you're completing this sentence here, or this explanation. The wind causes the plastic cups to turn. This causes the spindle and magnet to turn. And I think probably everybody had the idea of the magnet turning for 1 mark. After that, quite a few of the explanations weren't very good. So you need, this is again a fairly standard thing that you need to be able to explain. Try and keep it really simple, and remember that the critical thing here is that you've got to have a changing magnetic field, or if you want to use the more technical term, a changing magnetic flux, in order to induce an EMF. So changing magnetic flux, and you have to say where it is, so it's through the coil of wire. If you'd had said, so changing magnetic flux through the wire, then if you look at the diagram, well, there's wires there that probably, well, they're definitely not going to get an EMF induced in them. So again, that's just about being really specific. In a different question, a different mark scheme, it might not have mattered, but you need to mention that it was the coil of the wire here. So changing magnetic flux through the coil induces an alternating EMF. The reason why that's important is because it says up here it's an AC voltmeter. If this was inducing a constant EMF, the voltmeter wouldn't read anything. So again, it's very picky, but you need to talk about an alternating EMF or a changing EMF in order to get the mark there, and then that causes a reading on the AC voltmeter. That last point isn't necessary for the 3 marks. So magnet turning, so you get a changing magnetic flux or a changing magnetic field through the coil, and that induces a changing EMF or an alternating EMF in the coil. Okay. Why does the voltmeter reading increase as the wind speed increases? Again, the mark scheme was really picky for this one. The magnet spins faster. There were quite a few answers that I think just said the magnet moves more, or something along those lines. It needs to be really clear exactly what's going on, and it's the spinning, isn't it, that's producing the alternating EMF, which is going to be read on the AC meter. So again, that's the AC thing is a bit important in this one. The other way of answering that would be to say there's an increase in the rate of change of magnetic flux. Again, it's not that there's a change in the magnetic flux or there's an increase in the magnetic flux. It's an increase in the rate of change of magnetic flux, because induced EMF is proportional to rate of change of magnetic flux. Again, you just got to be really pedantic about the wording for that particular question. Then it kind of gets simpler again. So one way that Sue can modify the design to make the gauge more sensitive. So it's that standard thing of how would you get a bigger induced EMF. So more turns in the coil. You could have stronger magnets. It's just those 2 things. You can't have... there was somebody put an answer in about using gears to make the magnet spin faster, which I really liked, but I don't think that that would work, although I've thought quite hard about the physics, so I'm not absolutely certain. But more turns in the coil, stronger magnets are the obvious answers. How could Sue make the gauge monitor and record wind speed automatically? You just need a data logger. You can say computer there, but data logging is what we use in physics for that. And I think the reason why some of you didn't get that question right is just not having seen that sort of question before. It's really common to get asked about how you automate something, automate measurements, and the answer is always use a data logger. The question sometimes, if Sue wanted to measure the wind speed over 24 hours, how might she do that? When the answer is, well, you use a data logger. Sometimes the question is, why would a data logger be better than a person? And then it's just simple answers about, well, a person can't stay awake for 24 hours, that kind of thing. Right, structure of a transformer, explain how it works. Again, a fairly standard explanation here. It's just about the accuracy of your explanation. So the word changing, again, is absolutely critical to this explanation, because remember, if you do this with a direct current, nothing changes and the transformer doesn't work. So you need changing current in the primary coil, causes a changing magnetic flux in the core. You'd be okay with changing magnetic field in the core there, but flux is better. And that goes through the secondary coil. That's quite important, because the flux in the core isn't important. It's that the flux goes through the secondary coil because it's in the core. So changing current in the primary coil causes changing magnetic flux in the core, and through the secondary coil, the changing magnetic flux in the secondary coil induces an EMF in the secondary coil. And again, there were some things where it just said induces EMF. Yeah, is the EMF induced in the core? Well, yes it is, that's what causes eddy currents. Is it induced in the primary coil? Yes it is. That's why, subtle things to do with the design of the transformer. Neither of those are relevant. It's the induced EMF in the secondary coil that makes the transformer work. Okay, so again, think about exactly what it's asking you and try and be really accurate with your explanations. This was just a straightforward calculation about number of turns on the secondary coil. I think most of you got that right. If you got it wrong, just have a look at it and work out why. This one, we didn't do this practical. I'm sorry about that. That was because the balance wasn't working. We need to get some batteries for the balance. If you want to have a go at that at some point, we have got the kit for it. It's quite a nice little experiment. You can increase the current through the wire, and that increases the force on the balance, and you can measure both of them and get a directly proportional relationship, because F equals BIL and things like that. In making that calculation, the thing that a few people, well, there was a couple of things that got missed. One was that some people didn't convert this mass in kilograms into a force in newtons. And I know that in a mechanics context you would have got that easily. It's that business of watching out for those little simple things even when the context gets difficult. And quite a lot of you use 10 newtons per kilogram to do the conversion. And this is an A-level question, so there's an expectation that it is 9.81 rather than 10 that's used as your conversion. Apart from that, I think it was okay. Almost everybody coped really well with the fact that this is in milliteslas and that the dimensions are in millimetres, so that was great. Again, these two questions mostly were done fine. If you didn't get it right, have a look at the mark scheme. It's kind of self-explanatory. You just need to get the right question and make sure that you're careful with the units that you're working with, that sort of thing. And again, this one, calculate the magnetic force on side AB. Again, that was done well. If you made any mistakes with that, have a look at the mark scheme. B, the correct answer is C. There's no magnetic force on side BC. But some people went for B. I don't know whether it's a bit confusing, isn't it? Because it's A, B, C, D, N, S, A, B, C, A, B there. I can see why it might be easy to get confused. If you just got muddled up about which side it was talking about, then just have a look at it. If you were clear that it was this side BC, that it was being asked about, then the reason there's no force on that wire is because it's parallel to the field lines. These wires are cutting the field lines, which would be going straight across from north to south. That side doesn't experience a force because it's parallel to the field lines. It's not cutting any of them. And then there's this question about it asks you to sketch 2 complete loops of magnetic flux which pass through the secondary coil. So I've drawn those in here. Those were done correctly, but there's nothing to prevent you from getting a ruler out and doing a neat job. But it wasn't required for this particular question. Just watch out for that though. 2 things. 1, model good practice for your kids. You will get sick of their scruffy books, and if you're scruffy yourself, well, maybe it won't bother you that their books are scruffy in that case. But if you want them to do work that is neat and moderately legible and you can see their diagrams and they label them and all the rest of it, then you need to model good practice for them. And then this one, I'll do this for you now. So what you're trying to do here is you're being given the EMF already and you're trying to do the magnetic flux. That's a little bit harder than what I did in the class, because in class I gave you the magnetic flux and you had to work out the EMF. This one's backwards. So at this point here, the EMF is a maximum, so that means that the gradient of the magnetic flux line needs to be a maximum and it needs to be negative. So there's a line going down like that somewhere at that point. And then this is the negative, maximum negative EMF, so that gives you the maximum positive gradient on the magnetic flux line. At this point here, the EMF is 0. If the EMF is 0, then the magnetic flux line must have a gradient of 0. And if I look at the direction of these 2 lines, that must be a negative value. Now, I could make it the same amplitude as the EMF, but it doesn't matter, it's only a sketch graph. I'm actually going to make it different, because for me, I find it a little bit easier to draw like that, but you might not. At this point here, the EMF is 0, so the magnetic flux gradient must be 0, so that's going to be up at this maximum point here, so it's going to be flat there. So we've got a trough there, a peak there, a steep line going up there, steep line going down there, and then it's a sine wave, and they're quite awkward to draw. I let you off with the really triangular ones, but if they're too pointy you might lose marks in an exam paper. So how do you do this? So what you need to do is that point and that point, halfway between them, go about 2/3 of the way up or down, make a mark. Do the same here, so that point and that point, halfway between them, 2/3 of the way up. Okay, same here, there, between there and there is here, and there's going to be one more, isn't there? So something like that. I need to do it here as well, so halfway between those, up 2/3 of the way, and that's going to be a maximum. Right, now I've got those points in, it's pretty easy to draw. And they were quite generous in the mark scheme, because they allowed you to be, as long as you were out of phase by 90 degrees, they awarded the mark whether you were out of phase by negative 90 degrees like mine is, or by positive 90 degrees. Okay, but that's how to do that question. It did get quite hard at the end, this exam, didn't it? Right, okay. C is the most difficult question on the paper. So what are you trying to do? I know most of you tried to answer this using the formula NP over NS equals VP over VS. You can't do that here because it's actually saying EMF across the coil over turns of wire in the coil is equal for primary and secondary. So although it's not written like that, the stem of the question is telling you that NP over NS equals VP over VS. So you can't use that equation to explain why. It's just a circular argument. So how do you do it? Right. So first thing is to say you get the same rate of change of magnetic flux through the primary and the secondary coils, because all the flux is through both of them. So if the flux is changing, the rate of change is the same for both coils. Right, and the rate of change of magnetic flux is delta phi over delta T. So that's the same for both coils. Right, but the coils have different numbers of turns. So they have different flux linkage. Same rate of change of flux, but because the number of turns, n, is different, you get a different flux linkage. Okay, so for the primary coil, the EMF in the primary coil is equal to NP multiplied by delta phi over delta T. And for the secondary coil, it's exactly the same, except it's NS. But delta phi over delta T is the same for both of them. Okay, so that means that EP equals, I'm not explaining that very well. If we divide this equation by NP, we get EP over NP here is equal to delta phi over delta T. And if we do the same with this one, we get ES over NS, so divide both sides by NS, ES over NS, is equal to delta phi over delta T. And that delta phi over delta T is the same for both of them. So this must be equal to this, and that is EMF across the coil divided by number of turns in the coil. Alright, so same rate of change of magnetic flux through both coils, but different numbers of turns, so the potential difference, or the EMF, divided by the number of turns is going to be the same for the primary coil as it is for the secondary coil. Okay, if that is going over your head, do not worry about it. That is right at the absolute limit of A2. Okay, it's a really difficult question to answer well. There are some other ways that you could answer that, but have a look at the mark scheme. If it makes sense, that's great. If it doesn't, don't worry about it. Okay, that's the one thing on the whole paper that I'm not bothered at all about whether you understand or not. Alright, so back onto something a bit more sensible. Explain why eddy currents are set up in the core and suggest why this alters the flux in the core. Well, particularly, there's actually two questions here. So explain why eddy currents are set up in the core. So that's definitely doable. Okay, so the difficulty here is that you've got the primary coil, you've got the secondary coil, and you've got the core. You've got magnetic flux in all of them. You've got stuff going on that is due to the way the transformer works and stuff that's going on that's trying to stop it working. I understand why that's confusing. Okay, so can we cut through it? Alright, so when the transformer's working, you've got changing magnetic flux, haven't you, caused by the primary coil. So that means there's a changing magnetic flux in the core. Yeah, the field lines are going through the core. You're changing the current in the primary coil, so it causes a changing magnetic flux in the core. Now, if there's a changing magnetic flux in the core, that's going to induce an EMF in the core, because the core is made of a conductor. That causes a current, and those are the eddy currents in the core. Can you see this is all in the core? So changing magnetic flux in the core induces EMF in the core, causing currents, the eddy currents, in the core. It's the same explanation for why you get an EMF induced in the secondary coil. That would be the same wording but a different place. Changing magnetic flux in the secondary coil induces an EMF in the secondary coil, causing a current to flow in the secondary coil. Yeah, so it's the same explanation, but you're just relocating it. And then why does that alter the flux in the core? So the second part of the question here. Well, the eddy currents then create new magnetic flux. Every current has a little magnetic field around it, a little bit of magnetic flux around it. So eddy currents create new magnetic flux, which opposes the change that caused it. So it's all that new magnetic flux, the new magnetic field, is always going to reduce the main magnetic field. Okay, so the eddy currents are going to create little magnetic fields, and what they're going to do is they're going to reduce this main magnetic field that you drew in this question. Alright, and have a look at the mark scheme, but it is only 2 marks, so any of those points really would be okay. And lots of you got the opposing thing, which was great. So even in the middle of not being quite sure what you were doing, you were still thinking, aha, Lenz's law. Yeah, it's the opposite direction. Whatever's going on, it's the opposite to the change that caused it, so that was nice. And again, if you get stuck like that, don't be afraid to just state the law. Lenz's law states that the induced EMF, or in this case the induced magnetic flux, opposes the change that caused it. State and explain how the core should be constructed so as to reduce eddy currents. So there's that stock phrase again, laminated iron core. So this word laminated would have got you the mark. It is state and explain, so you might want to go into a little bit more detail there. What does laminated mean? Well, thin layers of iron and an insulator. So it was 1 mark for thin layers or laminated, 1 mark for the idea that the bits of iron were separated by an insulator. That would have been your 2 marks. Or you could have done the explain bit. Why is laminating it, why does that help? Well, it increases the resistance of the core, so it reduces, it more or less stops the eddy currents flowing. So there's about 3 or 4 different things you could say there. You only need 2 of them for the mark. Right, okay, I hope that was helpful. There will be some electromagnetism questions in the second A-level paper. None of them will be as hard as the back end of that formative test, but apart from the very hardest questions in there, those other A-level questions, they're fair game. So don't worry about the very most difficult ones on that last page, but have a look at the other ones, and in particular have a look at what you've written and compare it to what I've written, and think about the differences in how specific your explanation is compared to mine. And that's the difference really. I could see from your explanations that you more or less understood what you were trying to say, but in quite a lot of cases you weren't able to say it accurately enough to get all of the marks. So a little bit of work on that and you'll be absolutely fine on that second A-level paper. Okay, good luck.